Hello students, we're continuing with our study of waves. What I'm about to show you, superposition of waves, is something that you will see in the lab I assigned. It's lab 14B, the pivot lab, and what I suggest you do is take a look at the lab before continuing with this video. Once you've at least looked at what's in the lab, then come back to here where I'll talk about what's going on in the springs and so on that you're going to see in the lab. All right, so let's take a look at how waves superimpose. I've got a video here which is of a simulation, and in the simulation, you have a wave that is coming from the right, and it's going to superpose with a wave that's going to the left. So what you need to think of is that this is a single spring, and so this is showing one wave on the spring, this is showing another wave on the same spring, and then down at the bottom here you get to see what happens when the two waves collide with each other, quote unquote. Okay, so let's see what happens here. Okay, you can see that the two waves are about to hit each other. Now they're on top of each other. And now they are moving away from each other. They've gone through each other. So looking at this simulation, it's telling us a few basic things. First of all, when waves go through each other, like this wave has passed through this wave, the shape of the waves is unchanged. This will happen anytime you have what's called a linear medium. A linear medium, like a well-behaved spring or a well-behaved rope, or ocean, the surface of a pond, those waves will go right through each other without changing each other's shapes. So that's a linear medium. Okay. Now the next thing that I want to show you, let's back this up, is that when the wave peaks, and so vocabulary, this is called the peak of a wave. This is the trough of the wave. This I sometimes call the zero crossing of the wave. So when the peaks of two waves are aligned, the amplitudes, which let's say the amplitude like this plus this amplitude here, the amplitudes add up. So you have this amplitude plus this amplitude equals that amplitude. All right. Now the next thing I want to show you is that when the peaks and troughs are aligned, so this trough is aligned with this peak. See, this is a negative amplitude part of the waveform, and so you have cancellation. And here you have a peak lined up with a trough, and you get cancellation. Now, actually, there is a moment where this is perfectly flat, but the time steps in the simulation are too coarse. I can't quite show you when it's exactly flat. But in the pivot lab, I think you can see that. You can actually see the spring becoming almost perfectly flat. Okay, so this is called destructive interference, whereas this piece right here would be called constructive interference. All right. Now, there's something that I bring up in the lab. There's an issue which I want to talk about, and has to do with energy. Waves carry energy in them, and the energy it comes in two forms. One is that the springs move, right? So the right here, this piece of the spring is moving upward, and here this piece of the spring is moving downward, and that's kinetic energy. So the material, right, the mass of the spring has a velocity, and the kinetic energy for a little piece of spring is 1/2 mv squared. So each little piece of spring, when it's moving, or I keep saying spring, but it could be rope, it could be other materials, have a certain amount of kinetic energy. But that's not all. You see, when the spring is flat, okay, it's flat. But when it's pulled up like this, it's been stretched, right? This stuff here has been stretched. And so when you stretch a spring, you get spring potential energy. So you have kinetic energy and potential energy. All right, so now the question is, where did all of that potential energy go, right? So it seems like the potential energy has disappeared. And the question is, where did it go? All right, so I need you to think about that. Okay, so we've looked at how superposition happens, and there's quite a bit of vocabulary that is associated with this. So one piece of vocabulary is the word interference. And so interference means when the waves superimpose in such a way to make them, here we have them adding. And so when they're adding like this is called constructive interference. And the two waves put together make for a bigger wave. And so we say that the waves are reinforcing each other. Another phrase that comes up quite a bit, particularly with electrical engineering, is that right, let's say you're graphing something, a sine or a cosine, and you have two different waves that are offset, right? The difference from here to here is called the phase difference between the two waveforms. The phase difference between this one and this one is 0. When the phase difference is 0, we say that the two waves are in phase. On the other hand, here you've got destructive interference, right? So what we see here is destructive interference. When this is happening, it's called cancellation. And if you draw two waves, two sine waves, and you're doing this, we say that this one and this one are 180 degrees apart. Their phase difference is 180 degrees. And we also say that they are perfectly out of phase. So 180 degree phase difference is also known as out of phase. So far, all of our examples have been one-dimensional. So, for example, a wave going down a spring, or a wave traveling down a string. But of course, waves can propagate in 2 dimensions, like they do on the surface of a pond, and they can propagate in 3 dimensions, like they do waves coming from my mouth, right? My sound waves are propagating in 3 dimensions. Light waves propagate in 3 dimensions. So when you have 2 sources of waves propagating in 2 or 3 dimensions, you get interesting patterns. They're called interference patterns. Now, for these interference patterns to look like they do here, the 2 wave sources have to have the same frequency or the same wavelength. And what you're seeing here, I think this picture was taken using a setup that had a pond, a small pond of still water, and then two little sticks on an electric motor going up and down, bloop, 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 making ripples in the water. And when this photograph was taken, you can see that the waves were propagating circularly. The fact that these are circles means that the wave speed is the same in all directions, and under normal circumstances that's the case. And but now what happens is that the wave troughs and peaks are matched up here, along this line here, and along this fuzzy line here, this fuzzy line here, and I've labeled it destructive interference. On the other hand, the peaks and the troughs are adding up, are in phase here. The waves are in phase, and so you get constructive interference along this place here. So here they were, for destructive, they were out of phase. For constructive, the waves are in phase. And you can see that there's a pattern going on here, which I want to show you a little bit more about. So what I've brought up here is one of the PhET simulations. This one is called wave interference. And it's simulating sound waves coming from two loudspeakers. And this is in very slow motion. And right now I've got the sound off, so to speak. And I can now make the sound, quote-unquote, sound come on. You see that the loudspeakers are pushing, pulling, right? And so it's, we're going to talk about sound a little bit more later, but when the loudspeaker goes forward, it's compressing the air, and when the loudspeaker pulls back, it's decompressing or rarefying the air. And so you see waves of pressure happening. Now, maybe it's interesting to just turn off one of the loudspeakers. Let's turn it off. Okay, is it off? There. And so you could see that the waves are circular, which tells us that the wave speed is the same in all directions. That's good. And now when I have the second loudspeaker on, you could see that there is a pattern here, and the along here, let's do it this way, there's destructive interference here, and there's constructive interference here, and here, and here. Now, the pattern changes depending on how far apart the two loudspeakers are. So, for example, let's make them further apart. And let's see what happens. Now, when they're further apart, you get more fringes, so this is called more zones of destructive and constructive interference. Now, another thing that you can do that will change the pattern is decrease the wavelength or increase the frequency. Increasing the frequency causes the wavelength to decrease. So now let's see what happens. So increasing the frequency or decreasing the wavelength also causes more zones of constructive and destructive interference. Now this simulation shows a few other interesting things. Let's reset it, and let's go to water. Okay, so now you can see that water waves do the same thing, which I guess is not really a surprise. And finally, this is actually kind of interesting. Let's make it go. All right, so now this is simulating light waves. Now, I said this is in super slow motion. That was for super slow motion for the sound. They're like ultra slow motion for light waves because light waves are really fast. Also, the interference patterns here are much magnified. If you tried to do this with two green lasers, you would have this pattern, but the thing is that the fringes would be very, very close together. And also, I should be a little careful because for this to work with lasers, either the two lasers have to be locked to each other, or what you really need is a single laser that's been set up to produce two outputs. But when you do this experiment with lasers, you can put a screen over here. Maybe in one of your advanced labs, you'll get to do that. And if you have the two laser outputs further apart, let's see what happens. Look at what happens on the screen. You see that this pattern of bright and dark, which is constructive, destructive, constructive, the pattern gets more tight. They're closer together than when they are close together. So let's say I put the two lasers close together. Now let's take a look at the pattern on the screen. It's destructive here, constructive here, and destructive here. I have one more thing to show you on the topic of interference patterns. What you're seeing here is just a series of circles, and what I'm going to do is I'm going to transparently overlay on top of that an identical series of concentric circles. Let's do that. Now this pattern here was described by a French mathematician. His name is Moiré, and so these are called Moiré patterns. And they do a good job of representing interference patterns. So it's like I have a snapshot of two wave sources frozen in time, and right now the two wave sources have been running for a while, and the waves have been propagating outward, and there's no interference between them. But if I offset the two sources, then you get zones of this is destructive interference. This is where the black and the white are coming together. So it's as if it's like the wave troughs and the wave peaks canceling each other out. And so this represents destructive interference, and then this represents constructive interference. And one thing that's really useful about this is look at how the spacing of, let's say, let's look at constructive. So right now we have constructive. Let's use red for constructive. Now, when the two sources are further apart, what happens? The zones of constructive interference have now moved closer together. See now they're here, and here. So you get more zones of constructive interference per unit of angle. Now, so far, when we're talking about interference patterns, we're talking about two sources with exactly the same frequency, exactly the same wavelength. But you can also get an interesting interference effect when the two frequencies are a little bit different. And that's called getting interference beats. The frequency of the beats is given by this formula here, which says that if I have two frequencies, frequency 1 and frequency 2, then you're going to get an effect where they get louder and softer, louder, softer, and each time that happens, that's called a beat. And the rate at which the beats happen is given by the absolute value of the difference of the two frequencies. So it doesn't matter whether this frequency is higher and this one is lower, or the other way around, this one is higher and this one is lower, because of the absolute value sign here. Now, what I want to do is make you watch this YouTube video. It's going to be the next one in my playlist. Also, what I'd like you to do is watch the video that comes after that, which is going to be about the Doppler effect. So watch the two videos on YouTube, and then we'll come back to these notes.